Hey everyone, welcome to Project 2 for Operating Systems. My name is nick.desanctis and I'll be taking you through an in-depth discussion on everything you need to know to get started. So, let's begin by talking about memory management. For this project, you'll be working on an entirely static C++ library rather than tinkering with the kernel directly. This library will essentially be a replacement for the new keyword in C++, and other programs that want to make use of the functionality you develop will be able to include and link with this library. Naturally, since this is a project about memory allocation, you'll want to make sure you're really comfortable with dynamic memory, pointers, and pointer arithmetic. There are some resources linked here in the discussion slides that might help you brush up. Now, let's talk about the distinction between words and bytes. Many functions you'll have to make in this project will have their units listed in words rather than bytes. But essentially, words are just some whole number multiple of bytes. The constructor for your class will have a word size parameter directly, which is an unsigned int. The word size will come into play quite often, so make sure you keep track of that somewhere in your memory manager class. There are several situations where you'll want to convert between bytes and words, and you can use knowledge about the size of a word to convert from words to bytes as follows. That's number of words times word size equals number of bytes. For example, if you have a word size of 7 bytes and there are 10 words, that's a total of 70 bytes. Now, conversion between words and bytes doesn't always work out so nicely. For example, maybe you have a word size of 4 bytes, but the user is requesting 14 bytes. In this situation, we have 3 full words, that's 12 bytes, with 2 bytes left over. And 2 bytes, that is, because 14 modulo 4 is 2. And we can't very well just disregard those 2 bytes, so we just give an extra word, and that's a total of 4 words. Now, technically, there's some internal fragmentation going on here, or at the very least, something very similar to it, as that fourth word will have a whole 2 unused bytes in it. That's perfectly fine here, though, and it does not count as a whole. Speaking of wholes, let's talk about blocks and wholes. Tracking these properly will make up the majority of the project. Blocks are just allocated portions of memory, while wholes are portions that are available to be allocated. So in this project, your job is essentially to hijack a big chunk of memory off the heap and rent parts of it out to your user. In other words, you are the middleman. Anyway, keeping track of your rental properties, blocks and wholes, will be best achieved through some kind of data structure. So there are quite a few ways to do this, and you'll want to spend some time thinking about what intuitively makes the most sense to you, but there are viable ways to achieve functionality using linked lists, vectors, and heck, even maps. And if you're like me, you might get extra fussy over the efficiency and elegance of your code, but just know that any extra time you spend optimizing your time complexity and whatnot is time that could be spent making sure your project is actually functional. Not saying I regret the way I chose to approach the project, but just be aware that you aren't being graded on your design skills here, so prioritize functionality. Also, since this is C++ instead of C, you now have access to legitimate object-oriented programming. I highly recommend using classes and OOP to keep track of whatever you want to keep track of. At minimum, you'll probably want to keep track of the offset of a block as well as its size. Since classes can help you keep track of more than just those, I'd recommend using them as opposed to something like a standard pair object. Once again, though, you aren't being judged on your design skills here, so do as you see fit. Next, let's talk about void pointers. Wait, what? A pointer that points to nothing? Well, yeah, kind of. Void pointers are pointers that don't have a type attached to them. These can be really useful in keeping your code flexible in different use cases. If you know the idea of templates, it's kind of like that, but with pointers. Particularly, this can be helpful in allowing the user of the program to allocate objects of whatever type they want when using your library. With that said, a void pointer is ultimately just a pointer. If you know what kind of data it represents, all you have to do is cast it to the correct type. And conversely, you can cast from a different type to a void pointer if necessary. And speaking of types, types matter quite a bit. You'll need to have specific byte size types in arrays. So if you're ever asked to use a type with a specific number of bytes, or given a limit for how many bytes something can be, you can reference this big table here. However, especially since specific byte size types throughout this project are quite frequent, you may appreciate the increased clarity that uint x underscore t types provide. So what's a uint x underscore t type? Well, these types are always unsigned integers of x bits. So a uint 8t is 1 byte, a uint 16t is 2 bytes, etc. And now at some point you'll be asked to instantiate your memory block with a 1 byte type. So you could use a uint 8t there, just as an example. Now there's a file you'll want to include in your header file to gain access to these types, but they can vastly increase the clarity of your code, so I recommend making use of them. If you don't want to use those though, an unsigned char also represents 1 byte, and that's a valid way of doing it as well. That's well and good and all, but what exactly are we doing? Oh, it's actually pretty cool. We're going to make a memory manager class that acts as a replacement for the C++ new keyword. The user will then initialize a memory manager object with some size in words. They can then allocate some size in bytes, and that will return a pointer to the start of that allocation in memory. And when they don't need that memory anymore, they'll call the free function, which you'll also be implementing. That'll free the memory up to be allocated again. All right, next I'm going to go over the declaration signatures for all the required functions. So first off, the constructor. This will take in the word size as an unsigned int, as well as a C++ function object. So this is just going to be a function, basically. And this function returns an integer and takes in an int and a void pointer as arguments. So in practice, you're just going to be passing in the name of one of the allocator functions that I'll be talking about later, and assigning it to the allocator variable that you have in your memory manager class. Next here, the destructor is listed because there's like a 99% chance that you dynamically allocated some memory in this project that you're responsible for deleting. So this destructor should just ensure that the memory is properly deleted once the memory manager object falls out of scope. Then initialize, this will take in a size in words and we'll get the initial block of memory from the heap. This block will be of size in words times word size amount of bytes. Now, if initialize is called on an already initialized memory manager, then shut down and reinitialize. Now, for that matter, most of your functions should not work before initialize is called on the memory manager object. So be sure to check for this in your functions and return the relevant error where necessary. Then shut down. This will clear all data, free any heap memory, clear your data structures, and reset member variables to their default states. Then we have getList. This is one of the most critical functions to understand in this project because of how frequently it's used in other functions. So this returns a void pointer to the start of a 2-byte array that contains the list of holes. So the first element should be the number of holes in your block, and the following numbers are going to be pairs representing the offset, as in where the hole starts relative to the beginning of the memory block, and the size, as in how long or how large the hole is. All right, moving on, here we've got allocate. So this function will take in a size in bytes, and this is where you'll have to calculate the number of words needed based on the division and modulo we talked about earlier. Once you have the number of words to allocate, you'll be calling one of your allocator functions to figure out where in your block to allocate the memory. As a result, this function depends on both the logic that you implement in your allocator function and the logic you implement in getList. So if you have any issues here, you may want to find ways to isolate each of those functions out to figure out where the problem is. Allocate then just returns a void pointer to the beginning of the newly allocated memory block. Then free, this will take in an address that should be somewhere in your memory block. this should point to the beginning of the allocation that you want to be freed, the address parameter that's passed in, that is. Remember that you aren't actually freeing any memory from the heap here. You're just marking that space of your giant memory block as available to be allocated. So because of that, you won't need to call delete or anything like that. You will, however, want to make sure that you update your data structures accordingly. So for example, if you have an allocation sandwiched between two holes and you want to free that allocation, you'll want to make sure that freeing it condenses all three of those holes into one new hole. So consider the various cases that might cause holes like these to be combined, as well as cases where new holes might appear. So then set allocator, this will just set the allocator variable in your memory manager class to the function object that's passed in. So that's going to be either best fit or worst fit, and those functions will be outside the memory manager class. You'll still be making those functions yourself, but they'll be standalone functions outside the class. Here, finally, dump memory map. This will take in a string that represents a file name and will write out a list of holes to that file. So how you go about getting this list of holes can vary, but using the getList function that you also made earlier might be a good place to start. You are not allowed to use C++ fstream objects for this. You have to use POSIX calls. So it should be noted that Windows does not natively support using POSIX calls, so make sure that when you run this function, you're running in Reptilian or some other Unix-based OS. There are also some file I/O resources linked here in this slide that'll help with learning about POSIX calls, which I highly recommend you make use of since they'll be super important to your implementation of Project 3. For now, though, just use the open POSIX call with these parameters, and remember to use the close POSIX call when you're done writing to the file to make sure that your change is saved. More about these parameters, though, in case you're interested. We use ORDWR to enable reading and writing. We use OCreate to create the file if it doesn't exist already. We use OTrunc to truncate the file to 0 bytes upon opening, and this has the effect of clearing the file out before you start writing bytes to it. So you'd want to do this to make sure that multiple calls to dump memory map have the effect of updating the existing list of holes in the file rather than appending extra ones on top of it. Finally, just pass in the number 0777 to grant read, write, and execute permissions. The combination of ORWDR and 0777 here ensures that reading and writing works whether the file exists already or is just being created. All right, here we go. Get bitmap. This function can give students a lot of trouble, and for good reason, because it can be quite complicated to wrap your head around because it demands quite an understanding of bitwise operations. So this function returns a void pointer to the start of an array of a 1-byte type, like a uint8t, that represents allocations in terms of words. So allocated words are represented as ones, and unallocated words are represented as zeros. Also, the first 2 bytes in this should represent the size of the array, which we'll go over in a second, and this will all be in little endian format. So just to go over an example here, so we can see how it works, let's say we're given this following list of holes. So our first hole starts at 0 and is of length 10, so we would expect to see our array start with 10 zeros, and indeed that is what we see here. Then our next hole is starting at offset 12 of size 2, so we would expect the 12th bit to also be a hole, and that would go on for 2 bits, and we do see that here. We know, however, that the space between 10 and 12 is not a hole. It's been allocated, and so those are represented as ones right here. Okay, so you can trace this sort of logic for the final hole, 20-6 if you like. But here in this example, we've got 26 words, but keep in mind that each byte in this represents a total of 8 words, since a byte is 8 bits, and we're representing each word with a single bit. So as a result, we'll represent this with a total of 4 bytes, and the last 2 words in this example will correspond to these 2 words here in this final byte. So then the next thing we're going to do is just mirror each byte individually, so byte-wise. So we're going to see that the bytes here all mirror to become this. The bits here all mirror to become this. And we don't really see anything in the cases of the 0 bytes naturally. But so the next thing we'll do after mirroring each byte individually is put those 2 bytes representing size to the front of the array. So since the size of the array is 4 for 4 bytes, we have to represent 4 with 2 bytes. And that looks like this. So we see that 1 here that's representing 4. Now, unfortunately, because this is little endian, we have to swap the order of these 2 bytes. So instead, it's going to look like this with the 1 over here. So now we can complete the array. So just to recap, after getting the initial list in terms of bytes, every byte gets mirrored, and the 2 bytes representing the size swap places, and then we combine that all together to get our completed bitmap. Okay, and that's get bitmap. The next functions are thankfully a little more straightforward. Get word size just returns a member variable from your class. Get memory start returns a void pointer to the beginning of the giant memory block you stole from the heap. And get memory limit returns the total number of bytes, not words, bytes that you can store in your giant memory block. This is also irrespective of the memory that's currently allocated. It's just the capacity of your memory block in bytes, and it's an unsigned int. And then finally here we've got the allocator functions. So these exist outside of the memory manager class, as in they do not belong to the memory manager class. These two are functionally very similar. For best fit, you're passing in a size in words that represents the size of the block to be allocated, and a void pointer that represents your list of holes. That sounds pretty similar to the output of getList, so make use of that if you'd like. You'll be finding the smallest hole that you can accommodate, your allocation, and returning the offset. That is, the start of the hole that will accommodate your allocation. So worst fit is the exact same as best fit, but it returns the largest hole that can accommodate your allocation rather than the smallest. So don't overthink what best and worst really mean here. They just mean the smallest and largest holes, and you'll be allocating to the start of the hole you find in both cases. And that's all of the function declarations, but here are some tips. So start early, start small. Also, ignore the printing functions at first. Dump memory map and especially get bitmap aren't super crucial for functionality and can really trip students up. So get your super critical functions working first. Initialize, shut down, allocate, free, get list, and the allocators are all more important than those 2 random printing functions. Besides that, though, it's important to try and understand things conceptually before you start coding things up. So plan out your data structures wisely. So some of these functions, like allocate, have a dependency on both getList and the allocator function to be correct. So planning well will be really helpful in avoiding huge bugs. Okay, here's a test case, which you can find in the huge testing file provided on Canvas. So here we're going to instantiate a memory manager object with a word size of 8 and a default allocator of best fit. We then initialize this with 26 words, and so we go and snatch a total of 208 bytes out from the heap to rent out to our users. So there's actually a typo here in this slide. 26 times 8 is in fact 208. But at initialization, the entire block is available to be allocated, and so we consider the whole thing a whole. Next, we'll do a bunch of allocations. These allocations in this example are being called with a uint64t, which is 8 bytes, thankfully the same as our word size. So the first allocation is going to be a total of 80 bytes, which is 10 words. The following allocation is going to be 2 words, the next is 2 words, and the final one is 6 words. And so we can see that we're assigning these to different variable names so that we have the ability to free them later. So allocate, our first allocation is going to go to the very left. We're assuming best fit here, although it doesn't really matter all too much since we have just one continuous hole throughout all of this. But we can see as we make 4 allocations that new allocations repeatedly get made directly to the right of the previous allocations. Then we'll free the first and the third arrays and see what happens. So In other words, we're going to go from this and we're going to free the first array and the third array. And as we can see, this is what we end up with. So the list of holes then, if we want to call getList, for example, should look something like this. So we have one hole here at an offset of 0 that goes for length 10. We have another hole starting at 12 that goes for length 2, and then the final hole that starts at offset 20 and goes for length 6. Oh, and yeah, these units are all in words here, by the way. As far as testing goes, the single best predictor of the functionality grade you'll receive on this project is the testing file provided on Canvas. I highly recommend looking at this file, understanding how it works, and what it wants from you. Now, let's talk about memory leaks a bit. Memory leaks are a very big concern with this project, of course, because we're dealing with so much dynamic memory. Submissions that have memory leaks of any kind will be marked 0 for the functionality portion of the grade, so make sure that your project does not leak memory before you submit. You can do memory leak checking using Valgrind, a command line tool to help detect memory leaks. We'll be going into a brief demo on that, how to use that later, but besides that, Valgrind will also help you identify other types of memory errors and can help you debug. You can also make use of GDB and compilation with debug flags to make the process of debugging things a little bit easier. So before we get to the Valgrind demo though, we'll just briefly talk about the report and screencast, and I won't go super in detail here because there's already a file on Canvas that lays out these expectations pretty explicitly already, but the expectations on these are pretty similar to the expectations for Project 1. So for your report, go through every single function, even the simple getters and setters, tell us why you use the data structures you did, how you calculated offsets based on the arithmetic with words and bytes, how you manipulate pointers, and overall how you manage blocks and holes with allocate and free. Also, explain how you use your POSIX calls in dump memory map and how you used Valgrind and our command line test file for testing and finding memory leaks. This report should be in man format with markup and must be below the 500-word limit. You can once again find a detailed list of the report and screencast expectations on the P2 Canvas page. In your screencast, you'll want to demo your program using Valgrind and the provided testing suite that's also linked on Canvas. You'll want to hit all the same points that you did in your report, just verbally, and make sure that you include a link to your unlisted video in your report and keep it to 5 minutes or less.
All right, now we can demo some Valgrind stuff. So here I am SSH'd into my Reptilian using VS Code, which is super, super handy, by the way. First thing we're going to want to do is install Valgrind. So to do that, we're going to do a sudo apt install Valgrind. And we can see I actually already had this installed, so it just said it was already the newest version. But anyway, yeah, I have my P2 up and running here. So that's command line test.cpp that's been SFTP'd into Reptilian, as well as the memory manager directory. You can see here in the memory manager directory, I have my source files as well as a make file. And so let's say I want to use Valgrind to check for memory leaks. And this is something that you're going to want to be doing repeatedly throughout the project. So I highly recommend that you do this by making a shell script. So let's make a file, call it build.sh, and go from there. So in this file, we're going to be running bash commands. So let's start by cding into the memory manager directory, and then running make to compile the library and build it as a static library. Then we'll go out to the previous directory, and here we can actually compile the command line test.cpp file. So let's do that as follows. We'll use standard equals C++ 17 -d-o. We'll name the executable test using command line test.cpp. And then we're going to link it with our memory manager library -l memory manager. Yeah, that sounds about right. Okay, then let's pass this executable through Valgrind. So that's going to be a Valgrind and then a dash dash leak check equals full, and a dash dash show leak kinds equals all, a dash s, and then the name of the executable. All right, so let's talk about these parameters in a little bit more detail. So the first parameter here, leak check equals full. This specifies that we want the most in-depth leak check possible. And the second one is going to basically show all four kinds of memory leaks. So that's memory that is definitely lost, memory that is indirectly lost, memory that is still reachable, and memory that's possibly lost. Now, you're going to want to care about all of these, as a fully functioning program should not have any of these issues. Finally, the dash S flag here, it's basically just like a verbose flag that tells it to be extra verbose about the errors it gives you, give you as much information as possible for debugging purposes. And yeah, so with that, we have our build.sh file complete. So let's save it and run it. All right, so we'll do a ./build.sh. And oh dear, it's permission denied. So we have to actually grant this file executable permissions first. So we'll do a sudo chmod plus x build.sh. And sudo didn't ask for a password because it just did recently. So that's fine. Then we'll try running the file ./build.sh and see what happens. So I compiled our library, and oh dear. So it looks like I actually have a bunch of errors in this file. So I am losing some kind of memory here. In fact, I've definitely lost 450 bytes. With that being said, how did I actually do on the command line test? Let's see, going all the way up through the verbose stuff. Wow, I passed all of the test cases of the library, despite the fact that I had memory leaks. And this sort of thing would be marked 0. So with that being said, I should probably go and fix that memory leak. So we'll just cd memory manager and then nano memory manager.cpp. And yeah, I'm not going to do that here, of course. I'm going to go fix this off camera and come back and show you what the completed output should look like. All right, now I believe I've gone and fixed the error. So let's try running this again. So we'll go back to previous directory, run our build.sh file. And let's see. Okay, so we had 394 allocations, 394 frees, all good. Everything's good. So yeah, this is what the successful output of the program passed through Valgrind should look like. And yeah, with that, I believe that covers all of the bases for Project 2. So with that in mind, just be sure to review the Canvas page, this discussion, of course, the project PDF, and any resources listed in those documents. And I wish you the best of luck.